Swayam Prabha. Digital India. Educated India.
Okay, students, today I will cover some more questions, and from there let's try to understand all the new design for the biosensors. So again, the tutorials for the biosensors. So let's try to understand all the questions. Okay. So first questions for today's tutorial is RCT. I think you can remember what is the RCT, and based on this RCT we can design the many biosensors, and we can characterize the biosensors, and we can develop some new technology. So let's come. What is the RCT? Is the RCT is the charge transfer resistance, right? Charge transfer resistance. So this RCT value will guide you, will give you lots of information for the biosensor development. So generally in the biosensor development, while you are adding the antibody, then target, then secondary antibody, like this step by step when you are forming the sandwich, like the sandwich ELISA, generally the electrochemical impedance value actually increasing. Why it's increasing? Because this all the protein stuff, they are non-conductive, right? Non-conductive, and if they are non-conductive, definitely resistance value will increase, RCT value will increase, right? This is the basic concept. So let's use them for the biosensor development, and let's try to think this, try to solve these questions, and just try to understand first the problem. See, the problem is why RCT value increase in the electrochemical impedance biosensors. So let's first draw, you can answer like this way in the exam. Let's draw the biosensor very basic surface. So first you have maybe one nanomaterial coated bare surface, bare, your surface is bare. So this is bare biosensor, sensor surface, right? There is no protein molecules. So as it is nanoparticles there, and your surface become, it is highly conductive, right? Highly conductive. So as your surface highly conductive, definitely RCT value will be very low, right? It will be very low. So you just think, then your impedance spectra, you can remember the x-axis, y-axis. X-axis we are measuring the impedance, right? Impedance of x-axis is the impedance of this is the real value, right? So here you can see the real impedance, right? So impedance of the real, and y-axis we are measuring impedance of imaginary value, right? And generally the unit is ohm. Okay, so in the bare sensor case, as it is the highly conductive, as you can remember, you may get very small RCT, like this semicircular region is the RCT. This is the RCT value, semicircular region, and there will be a straight line, right? This straight line is because of the mass transfer, right? So here mass transfer also very fast, and you very highly conductive. That's why you are getting very low impedance value. And you can just remember that the starting point, see the starting point, this is because of solution resistance, right? Solution resistance. So it will not start from exactly from this origin 0. So it will start from, there should be some resistance. This is because see, your sensor, I mean, there is some solutions, right? Some electrolyte you are using, some previous buffer or some real sample you are using. So, that sample resistance will be this one. Clear? Now, let us come the second modifications. So, your sensor surface has nanoparticle and maybe suppose it is the gold nanoparticles and your antibody is thiolated antibody. Gold and thiol have strong interaction. Your thiolated antibody you already conjugated on the surface. So, as this antibody come, and it has some non-conducting behavior with their protein. So, definitely your surface resistance, your surface impedance value will increase, right. So, what will happen then? Then you will get higher RCT. Right? So, this RCT2 will be for your, because of this antibody already on your surface, it will increase, and your straight line, these portions also will decrease, and this one will increase, this one will decrease, the straight line, because this straight line actually give you the information how mass transfer. This one give the information of mass transfer. So how fast your mass is transferring towards the electrode surface. Now, the third step. So, third step is your antibody you can now means when you add your real sample or your that contain your target, so this is your target, it will bind because of the antigen antibody interactions. So, definitely there will be again some hindrance of electron transfer rate. So, as they are protein, so electron transfer rate will again decrease and again impedance value will increase, right. That is why electrochemical means when you are developing this kind of immunosensor, your RCT value will increase slowly. So, again this is the RCT3 will be higher. So, RCT1, RCT2 and RCT3, see the trend will be like this. And like this way, so based on the impedance, that is why you can characterize your surface, right. Like if your sensor surface is highly conductive with this nanomaterial, then you will get the lower RCT, then slowly the RCT increases, then this is the confirmation that yes, your surface actually slowly binding with this material. That is why impedance value is a very good it is a very informative, and this all the information you can put together that your sensor is actually developing. This is a good method for the characterization of your sensor. Okay. So, these all the things you should keep in mind. So, this RCT increases in the electrochemical sensors. Let us try to think more like some details way, so that you can design some biosensors. Based on this RCT, let us design some biosensors. Suppose you have a sensor surface, just I think you can remember last time I taught you different pre-treatment, right, pre-treatment method. So, you can characterize your pre-treatment method by the help of RCT also. Why? Before the pre-treatment your surface may be not that much conductive, your surface was hydrophobic, not that much hydrophilic. So, after the treatment your surface become very conductive. So, definitely if you measure the RCT value, definitely you will get the small RCT, right, small RCT and higher the straight line. So, you can predict yes, your surface become clean. If your surface become not clean properly, if your pre-treatment method not effective that much, then you will get the higher RCT. So, before and after, so this one should be before pre-treatment, right, and this one would be after pre-treatment. Clear? So, like this you can characterize that your pre-treatment method how effective. And this is the electrochemical characterizations. Now, see, after the pre-treatment again you modified with some gold nanoparticle. So, what will happen if you modify the gold nanoparticle? So, this RCT value again will decrease or increase, again it will decrease. So, you will get again the very low RCT value, and this very long straight line you may get. This is because your surface become again conductive. That is why you are getting again the very low RCT value. Okay. So, this characterization technique, that is why definitely you should follow side by side your cyclic voltammogram. So, what effect on the cyclic voltammogram? When side by side cyclic voltammogram means, so first before pre-treatment, right? Before pre-treatment of your sensor surface. So, kind of cyclic voltammogram you may get. For example, you are taking the ferroferricyanide, like K2Fe CN6 or K3Fe CN6. So, here 2 oxidation stage and here 3 oxidation stage, right. So, if you take this couple and if you take the cyclic voltammogram, so for the before pre-treatment case, when surface is not that much conductive, maybe you may get something like this. This kind of cyclic voltammogram you may get. And if you see this oxidation peak potential and reduction peak potential, they are very far to each other, and you may get before pre-treatment this much RCT. So, you can correlate cyclic voltammogram and EIS. Okay, these two you can correlate. So, when your oxidation potential, reduction potential very far from each other, it means the surface is not that much catalytically active, not conductive, and you are getting higher RCT, like this way, higher RCT and delta E value very high, right. Now, you are using some pre-treatment like hydrogen peroxide, ammonia hydroxide and water mixture, right, 1:1:5. After this pre-treatment, what you can see, maybe you can see your cyclic voltammogram actually shifted, right. So, see your oxidation peak potential shifted left, and your reduction peak potentials also, maybe it should come like this, it should show near here, not toward very left, it should be near the right side. So, reduction peak potential, it should be actually like this, and delta E value will be less than, I mean it is delta 2 and if it is delta E1, so delta E2 value will be lower than delta E1. And after pre-treatment, see this is your this value, right, this is your EIS value. So, delta E value also decreasing, your RCT value also decreasing. So, this parameter from the CB and RCT value from the EIS, you will get lots of information on the surface. Now, after pre-treatment, you are modifying with some gold nanoparticle. So, what will happen on the cyclic voltammogram? So, cyclic voltammogram will be again shifted, right. So, it will be like this. So, it will be right very reversible. Means delta, if you think in this case it is the delta E3, so it will be very low delta E3. So, delta E3, delta E2, delta E1. So, this will be the sequence of that you will get from the cyclic voltammetry. See, I taught you at the very beginning, at the very first few classes, that time it was difficult to give you all the information all together at the same slide. But now during the tutorial, I am showing you everything all together, because I already taught you everything, all the like what is delta E value, what is cyclic voltammetry, what is the electrochemical activity. See, everything I am put together in one single slide. Now you can think like how you can correlate all the concept for one single problem, because it is so many information there in a single diagram. Now we can correlate. So, this is the sequence of the delta E, and you see the del RCT value, this is the RCT, right, this is the RCT. So, if you think this is the RCT3, this is the RCT2 and this one is the RCT1. So, in this case also sequence will be like this. So, RCT1 will be higher, then RCT2, then RCT3 will be very low. Like this way, you have to characterize the sensor surface very properly, and this is the very good electrochemical characterization. Electrochemical characterization of your sensor surface. You should follow this, and then you will have the whole idea about your surface. Okay, now put together your all information again to design a SARS-CoV-2 detection that is very timely. When these times you wanted to develop a SARS-CoV-2 detection say biosensor. Now you all you know already, like how to design a surface, how to clean the surface, how to make the very good sensor surface, and how to immobilize the antibodies. Now let's put together all your ideas for detection SARS-CoV-2. This is a very generic concept. This is a very general concept. You can use this concept not only SARS-CoV-2 for any target detections, because here, for example, I put this is just an example for SARS-CoV-2. So because here I maybe wanted to use a specific antibody, specific antibody for this SARS-CoV-2, right? Specific antibody for SARS-CoV-2. Now if I say this one for dengue or for malaria, maybe I can replace SARS-CoV for dengue or malaria, then just replace the antibody with dengue or malaria, then problem solved, right? That's why let's put together all of your ideas here. See, your biosensor can be like this. So I told, let's develop a lab on a chip. Lab on a chip means all your lab, all the development concept like sample processing, sample purifications, sample amplification, everything on a single chip. So let's design a chip like this. So this is called lab on a chip. So where first things, you here your sensor surface, right? Here one working electrode, here counter electrode, your reference electrode. So this is working, this is counter, and this is reference electrode. Now here actually you are modifying your antibody that is very specific for SARS-CoV-2. This antibody is very much this for SARS-CoV-2 that you immobilized here. Okay. Now you should have one inlet here. From there you can, inlet means here actually I wanted to integrate on microfluidic channel. Why I want to integrate microfluidic channel? Because easily you can handle the very low volume of the sample, no need any sample pre-processing, and you can try easily with this microfluidics. I just show you. So here maybe one inlet here, you are using your sample. So sample means in for the SARS-CoV-2 generally we are using nasopharyngeal sample or saliva sample, whatever you want, and that sample will contain your whole virus, and you are going to detect that virus. This is the SARS-CoV-2 is a RNA virus, right? So RNA virus. So in this case, maybe you want to detect the RNA, that you may think, or maybe you can detect the whole virus. So if you want to detect the whole virus, a specific antibody already immobilized here. So whole virus that may come here with the microfluidic channel, and it can bind with this antibody. So your working area here, your antibody here, so whole virus can bind here. Then you can take the impedance spectroscopy. Like if the virus bind on the surface, you will get the higher impedance value, right? But if you want to measure, like you want to develop a genosensor. Genosensors means you want to detect a DNA RNA kind of genetic material. So you know the SARS-CoV-2 is the RNA based virus, so you want to detect the RNA, not the whole virus. So in this case, so you have to I mean this upper part of the virus will dissolve, so that RNA you may get. For that you may have to use some other chemical. for this dissolutions of this virus. So upper part you have to dissolve. So some chemical you may need. That chemical, so you may need some kind of surfactant type chemical that will dissolve this virus. So that chemical you can inject here another channel. So it will then connect with this main microfluidic channel. So this generally microfluidic channel. So here you can make the serpentine. Last time I showed you already, right? So that it will get some time to mix the reagent with the sample. Okay. So from here your sample coming, right, and from here your reagent coming. So this reagent will react with the sample and you will get the RNA, and in this case your surface will be like this. So you will have some capture. So because this is the RNA virus, you want to detect the RNA. So on the surface you will have some capture RNA. Okay. Also you have to use some more reagent, so that because this is a very big RNA, you have to break this RNA. So all the chemicals you can try here. Okay. Then very specific RNA, maybe suppose it is 100 nucleotides or maybe 80 nucleotides you are using this capture. So this RNA will come and bind here. So specific RNA, so your target RNA will come and bind here. Target RNA means that come from your original virus. Okay. Then you will get the electrochemical signal change. In the impedance you may get the change. In the chronoamperometry you can show the change. In the cyclic voltammetry you can show the change. That all the concept I already taught you. See, in the lab on a chip, this is the whole systems on a single platform. So you should have a here one waste chamber, that is the outlet. One outlet you should have. This is the inlet and there is the outlet. Means the excess solution they should go through this channel and will store here. This is the basic concept I taught you. Just I am putting together all the concept in a single chip. So we can use the lab on a chip this concept for the detection of the SARS-CoV-2, and I taught you here two concepts at a time all together in a single slide. One is the antibody based biosensor you can develop, or maybe RNA based. So why I use the sometimes we want to do the RNA, because with sometimes we have to think about the very much specificity. Genosensor, they are very specific. If there is a single nucleotide change, maybe they will not bind here. They are on the electrocyte, they will may not bind. You will get the very specific sensor, and you will get very sensitive and very sensitive biosensors, very specific biosensors you can develop. So like this way you can plan a lab on a chip. So this is just for the example on SARS-CoV-2, but you can think some other virus detections also, like dengue virus, other detections, that also you can develop simply like this way. Okay. Now let's come the next tutorial questions is the maybe in the exam I can give you something like this, a schematic diagram. This kind of reactions case, let's try to gather all the information that is responsible for unwanted side reactions. Let's write. So you don't need to write the many sentences, just very basic things you can write. Unwanted side reactions means that can increase the background current, that is not actually your signal, that actually you don't want. So you want signal basically, right? So background you want very low, background you want low, signal should be very high. See, you can think, if I provide you this kind of reactions, you can first you just think this is a redox cycling reactions, right here, and you just see here the electrochemical and this one chemical, this one again chemical. So, this is the ECC redox cycling. Now, we can easily correlate your ECC redox cycling concept. So, what is the unwanted reactions? Unwanted reactions means without target, the reactions that happen, like say if there is no target, then this nanomaterial, this secondary antibody that coated nanomaterial, that will not be present. If this is not present, this NP, that is nitrophenol, will not converted to aminophenol. So, this will not be there, right. So, only your starting reagent will be your nitrophenol, right. This is already your sodium borohydride, this is starting reagent, and you are using this one, right, ferrocene plus, this is your starting reagent, right, because ferrocene plus will form the ferrocene 0 only after the whole reactions. So, these 3, 1 plus 2 plus 3, they should not react very fast each other, then only you will get the low background current, and if they react, then they are the unwanted reaction. So, you do not want these 1, 2, 3, they should not react, that is the unwanted reaction, right. It should not be happen, okay. It should be clear, number 1. Number 2, you have to mention like what is the unwanted, any other unwanted reaction. Now, so first you have to think about the total reactions, then one by one you can mention that your starting reagent. So, the main concept, the starting reagent that you used. So, they separately, they also should not react on the transducer. This is even glassy carbon electrode. So, this is one just a transducer surface. So, on that surface individually, starting reagent individually should not react, on sensor surface, right. So, if they react, then it is the unwanted reaction. So, if they react, that is the unwanted. The sodium borohydride is the starting reaction. So, if they react on the surface, that is unwanted. These reactions should not be happen. This nitrophenol is the starting reagent. If they react on the sensor surface, then that is the unwanted. This reaction should not be happen. And this ferrocene plus is the starting reagent. So, these reactions also should not be happen. And only ferrocene plus means if you take the one cyclic voltammetry of this one individually, nitrophenol, this one sodium individually, they should show very low current, not very fast current. So, this electron transfer rate should be very low. That they are the unwanted reactions. Okay. So, this is a very generic concept. What is the unwanted reaction and what is the role for the biosensor development. So, unwanted reactions case, if they are very high, then background current will be very high, right. If background very high, then signal to background ratio will be low, right. So, unwanted reaction that's why should be slow. Okay. So, this is the concept for today's lecture, and I taught you how to design a new biosensor based on lab on a chip, like just I gave you one example like SARS-CoV-2. So, design a biosensor. Let's put together all of your knowledge in a single platform, that is lab on a chip, that I taught you, right. And also I gave you many examples of signal amplifications, their unwanted reactions, that always you have to consider when you will develop, especially electrochemical biosensor. I think I told you at the very beginning, they are very sensitive, right. So, as they are very sensitive, then you have to consider that other reactions like the chemicals you are using, they should be, background current should be low. That is why you have to think very critically, otherwise you may not get very ultra sensitive sensor. Electrochemical sensor is really ultra sensitive, they are very ultra sensitive, but you have to design properly. If you can't think properly like how they are reacting each other, then you may not achieve your goal. So, that everything should behave properly on your single platform also, all the concept that you are getting from this course, let's put together all in a single plan and just think that you are getting higher current for the signal and lower current for the background. Then only you can get a very good electrochemical ultrasensitive sensor. Okay, so that's all. Thank you for today's tutorial, and next classes again I will show you many problems, how to think independently and design some new sensor for biosensor development. Okay, thank you.